get started. All right, well, thank you guys for having me out. It's really fun to be here. As Steve mentioned, this idea actually started here. It was, I remember it was the middle of the night in room 13 downstairs, sort of thinking of this and getting, I don't know, it was just really exciting. Stayed up all night thinking through this, and somehow it took, I don't know, what is it, 16, 17 years, but it was a crazy dream, and that was to do laser spectroscopy of the nucleus. An outline for the talk is here. I'll start off by just telling you a little bit about the history of this, and the sort of one isotope that makes this dream possible is thorium-229. Tell you about our contribution to this has been, many groups have worked on this, which was this idea of doping thorium into high bandgap crystals to give effectively a high density sample to find the transition. Tell you about, we lost our way a little bit for a few years, and then answer the question that I got asked at DAMOP for the last 15 years by everybody. I dreaded going to DAMOP because everybody would come up to me and ask me this question. All right, well, let's go and get started. My group at UCLA is kind of broad. And I just sort of mentioned the other experiments I work on. The sort of theme, if there is a theme, is I enjoy getting control of new systems. I think whenever you can do that, there's a lot of science and a lot of technology that comes from that. So we have work with a lot of chemists to develop what I call a quantum functional group. The idea is sort of a qubit you could stick to anything and it's still kind of a qubit. It's kind of a neat way of looking at quantum computing. I've worked with my colleague and constant partner in crime, Wes Campbell at UCLA, doing some trapped ion quantum information. A lot of my group works on getting control of molecular ions, and then the thing I'll talk about today is this thorium project. So probably don't need to go over this here, given the history of nuclear structure at Yale, but I'll just quickly set the stage, because not everybody thinks about nuclear structure every day. Now, the electronic structure of an atom, we're all very comfortable with, right? There's some potential, you have some constants of motion, you get these beautiful quantum numbers, you get these orbitals that fill according to a Pauli exclusion principle, right? And this is the Hilbert space of many of the experiments in this building. Many of us, especially in atomic physics, don't think about that. There's also the same thing going on in the nucleus. There's a potential, it's a little more complicated. But you get, these constants of motion. You get shells, orbitals that fill according to, in this case, two Pauli exclusion principles, because there's two types of fermions. But otherwise, it's sort of identical. There's angular momentum. There's principal quantum numbers. The reason we don't think about it is these energies are EV, and these energies are KeV to MeV. So in most of our experience, these are just frozen out. If you go to an atomic physics group and you talk about changing I, the nuclear spin, most people will be like, you can't change that. That's like just a number. You just kind of look that up, right? But you can. And so we'd love to get access to this in atomic physics, but we just don't have the ability to drive these transitions. There's one exception to that, though, and that exception came from experiments, was first identified in experiments done in 1976 at the Idaho lab by Kroger and Reich. They were looking at uranium-233 decay. It undergoes alpha decay. And you can, even if you don't think about nuclear decay every day, if you think about the thorium nucleus that is produced, it's going to be an excited state, right? The protons and neutrons were sitting here in the ground state of uranium, and then suddenly the potential of the nucleus changes, and they're all like, holy crap, I'm not in the ground state anymore. And they send off a bunch of gamma rays as they excite to the ground, or relax to the ground state. And by just collecting these gamma rays, you can piece together what the nuclear structure of the daughter nuclei is. And what they found is roughly shown here. So the ground state is a nuclear spin 5/2. And then this is just a rotational, I'll show you sort of band on top of this because this nuclei can rotate. There's another state with just a different angular momentum projection onto the symmetry axis and just another rotational band. And they didn't really see this state. They just sort of knew from the rotational progression that it should be there. And they said, oh, it should be less than 100 EV, right? Which was, given that in these other numbers, you don't even report that last decimal place, or that's pretty good. And so over the years, people did some more measurements and settled on about 3.5 E for this excited state. people went and looked for the transition, and no one found it. People thought they found it in the 90s, and then later realized it was nitrogen. And then the things sort of fizzled out. Until 2007, some beautiful work it was a Livermore, NASA Goddard, and Los Alamos collaboration, redid the Kroger and Reich experiment, but just with better spectrometers. And what they said was, oh, it's not 3.5 eV, it's 7.8. That's not that big of a deal from a nuclear physics point of view, but to the atomic physicists that looked for this, it takes the wavelength from 300-ish nanometers to somewhere squarely in the vacuum ultraviolet. So none of the previous experiments could have worked because they weren't done in vacuum. And so this re-energized everyone to go back and look at this. And the sort of motivation for this that most people in the atomic physics community took as the reason to go look for this. The real reason is everybody just wants to excite a nucleus with a laser. That'd be cool, but you have to pay the bills somehow. And so the way we pay the bills is like, this could be a really great clock. If you don't think about clocks every day, this is what we call the line width. It's just 1 over the lifetime of the state. And you can make something called the Q, right? It's just the line width or the frequency of the photon divided by the line width gives you an enormous number. The bigger that number is, the better clock you can make. If you just think about it as a Fourier transform, right? You just have some oscillating thing, right? It gives you a better clock. And so you want this number to be as high as possible. And so this was an estimate of what the line width was, and everybody said, oh, we should go build a clock. Now, there's a little more to the story that I think makes it a little more interesting than this. This is, I think, what I'm really excited about now, is the Q is one thing, but because this is in a nucleus, I think it can be a much more accurate clock than what we have right now based on electronic transitions. That's because things like black body radiation limit clock stability, right, or accuracy now, because you have to know the temperature of the room you're in, because there's stark shifts on these states from black body photons. The first E1 transition in thorium is at 40 keV. So hopefully black body is not anywhere near that. So black body is gone. And then you're dealing with nuclear magnetons instead of Bohr magnetons, nuclear quadrupole moments instead of electronic quadrupole moments. So the shifts are just smaller. So I think this can be a much more accurate clock. And just to give you the history of this a little bit, probably the first person to realize this, sort of mentions it in passing, was Eugene Tokaya from Moscow State in the late 90s. He wrote a series of papers that were very prophetic, I think, looking back now. There's a really important paper from Eckhard Pike and Christian Thom in a few years later where they said, really looked at making a clock out of this from a real atomic physics point of view. Later, a few years later, Andrei Derivienko with Alex Kuzmich looked at how you would do this with state-of-the-art optical clocks and predicted something at the time was sort of unparalleled performance. Our entry into this came along a slightly different axis. We proposed this idea of doping the thorium-229 into a solid. Now, let me tell you about how that might be a clock, because it'll be important later. So first and foremost, if you put a nucleus, we take a thorium atom and we just put it into some crystal lattice. Don't worry about the structure, just some atoms, right? The nuclear transition, to first order isn't really affected by things, right? It's when we think about doping or putting an atom into a crystal and we're driving electronic transitions, those are immediately ruined because of the chemistry of the crystal, right? Affects the electrons. But the nucleus, the first order doesn't care. Right? And so if we look at the Hamiltonian of this, sort of the first order is, it's still just these nuclear states that we can drive transitions toward. At the next level, if you do the right sort of crystal, if these have a high enough band gap so that you can get these VUV photons into this nucleus, you're pretty much always going to be working with these ionic crystals. There's no unpaired electron spin, so there's really no fine structure effects. Then that leaves just sort of a hyperfine interaction. This is basically just the Hamiltonian of NMR or Mossbauer spectroscopy. You can just multipole expand it. And the terms are pretty simple. There's a term you might call the chemical shift. It's just an interaction of the nucleus with the electronic wave functions nearby, right? And this just, you can think of it as a contact interaction, if you will. It's well known in NMR or Mossbauer spectroscopy. If you run the numbers, this gives you a shift of a few megahertz relative to sort of the ion, but it's just a shift if the thorium always goes into the same lattice site. It's a common mode shift. And then you can get a broadening that is temperature, or you can get a shift that's also temperature dependent, because, you know, effectively as you change the temperature, the crystal contracts. And so this is going to change a little bit. And that's sort of generically kilohertz per Kelvin. The next term, this this HM1 is just a dipole interaction. The thorium-229 has a nuclear moment, magnetic moment, and there's a lot of fluorines in all the crystals that have been used so far, also have spin. And so there's some interaction there. And that gives you of order a kilohertz to 10 kilohertz, sort of broadening of the transition. And then there's the electric quadrupole interaction. So the nucleus has electric quadrupole moment. The crystal clearly makes an electric field gradient, so there's an interaction. And that's the largest shift, but it's just a shift if everyone substitutes into the same site. And then it's also temperature dependent a little bit. And I hardly ever show this slide, but I'm going to show something new at the end of the talk, and I wanted to set this up. All right. And so what that led us to do was say, hey, you could actually dope thorium-229 into these crystals. And because you can put so stinking many thorium into it, I mean, you can get 10 to the 17, 10 to the 18, 10 to the 19. Like the signal to noise ratio in this leads to a clock of what I would just say broadly is remarkable performance, sort of stabilities that you really can't access any other way. Now, the truth is, this is not, well, so sort of the thing that paid the bills was to take, this is the time that defines a second for the nation and, replace it with just a crystal, right? So this is how we paid the bills, but it's not really what was the genesis of this idea. The genesis of the idea was to just solve this problem, which I call the needle in the haystack problem, which Steve anticipated, which was the nuclear physics measurement said the transition is somewhere between 140 and 180 nanometers. And the line width is something like 10 to 100 microhertz. Right? Finding a transition this narrow, even in the visible, is challenging, let alone in the VUV, where the sources are very, very rudimentary. But what this gives you is that enormous signal to noise. It was so large that we thought we could take a synchrotron beam and do the simplest experiment. You can find a synchrotron that is just widely tunable over this whole range. We could just, even though it's quite broad, there's so many thorium that you come in, you try to excite it, you collect the photons, you run the numbers, and the signal to noise looked like you could detect this signal. So that's what we set off to do. This was, I think like sort of right around the time, so I had the idea right at the end of my postdoc, and this was sort of the stage when I left Yale. Well, the first things we did at UCLA was to address this thing for this quote unquote magic crystal, right? It had a lot of requirements that were really fighting each other. You needed thorium to go into a crystal, which is hard because thorium's a big atom. A lot of things don't want it inside of it. It needed to be VUV transmissive, so it had to have a very high band gap, even when you dope thorium in it. Thorium-229 is radioactive. It's sort of an 8,000-year half-life. And so you don't want this thing to just sit there and glow. If you put radioactive things in materials, they often glow. That would be bad when you're looking for a tiny transition. And then also you didn't want it to just fall apart after a few days because of all these alpha particles just hitting it. So we spent a long time looking at crystals, studying them to solve these. The next challenge was that when we started this, thorium-229 was basically unobtainium. Our first quote, 3 milligrams was the minimum we thought we could get by with, was for $6 million. Right. But we had 60 days to think it over. So, But eventually, with a lot of help from our friends, we were able to solve this. Oak Ridge delivered to us that 3 milligrams of thorium. We were finally, after it was about 5 years of work, grow these first thorium-229 containing crystals. So the crystal that we settled on for now was this lithium, strontium, aluminum fluoride. The choices were driven by, it's really remarkable. The band gap is enormous, 10, maybe even 11 EV. It's the lowest, we had materials tested at Los Alamos. It was the lowest scintillator that they had ever measured. It's just sort of a remarkable material. And that strontium side is really big, and so thorium can just slip in there real easily. And I want to thank two people, Syed Mirzadeh, who was a radiochemist who is now retired from Oak Ridge. All of thorium owes him a great debt. He was very wise. Thorium-229, you pretty much have to have uranium-233 to recover it. Not many people have uranium-233 for reasons you could probably guess, but he had access to it, and he would sort of milk it when he had a chance and just kind of put it on a shelf for a rainy day. This was his rainy day. And Hans Jensen, who's just a wizard at crystal growth. The challenges of growing such small, high purity and high quality crystals are enormous, and we couldn't have done it without Hans. All right, so we grew our first crystals. This was over 10 years ago now. And we were already up at the advanced light source. It's a synchrotron in Berkeley. The beam comes in here. This was tunable over 140 to 180 nanometers. This is our sort of thorium experiment on this little cart. It's super simple experiment. There's just a crystal in the middle. The beam comes in. There's some PMTs here. There's some shutters. Then you illuminate for about half an hour because it's a very long lifetime. You close the beam shutter, open this up, and just see if the crystal glows. It's like dead simple. We were there waiting because we didn't know if these crystals would just fall apart after a day or two. Like, never really made anything like this before. And we didn't have that much thorium, so we didn't get a lot of shots. So the thorium was basically still hot from the oven, or the crystals were almost still hot from the oven when they arrived at the ALS, and we just ran and put them right in and started measuring. And we saw nothing, almost. There's some interesting things looking back, but we had no conclusive evidence of the transition, and so we made what we called our exclusion plot. This was what we did for many, many years. So on here's the possible wavelength of the transition. Here's possible lifetime. This blue region is where we thought it would be. We did some work with Eugene to sort of figure this out from the nuclear physics. And what we're able to exclude was shown in red here. That's sort of a 90% confidence. This exclusion was limited by two things. One is tunability. Despite being a synchrotron, we weren't allowed to tune it above 170 nanometers. And then even though there's a lot of photons in these synchrotron, the sort of spectral radiance is small because the bandwidth is very large. So we're limited by flux in a spectral sense. So we went back to UCLA and we built a VUV laser system. It was about 20,000 times brighter than the ALS. It's much narrower, that's why. And so it takes much longer to scan over this region. And there's a bunch of lasers here that get combined in a xenon mixing cell where we do some 4-wave mixing. And then here you can see that same chamber we had at the synchrotron. And this was a really, building this laser was quite an undertaking. I want to make sure and thank Christian and Justin for what they did. We knew going into this, it would take about 3 years to scan over this region, right? That's running like 24/7. And this is not a well-funded project because at this time, a lot of people, most of them appeared to work for funding agencies, didn't believe that this transition even existed. And so we had to solve all sorts of problems. Our first power meter measured negative power because the manufacturer had never actually used it and didn't think about the fact that you make photoelectrons when you hit things with VUV light. It was just all kinds of crazy stuff. We had to monitor constantly the mode spectrum of the laser because you don't want to scan across the transition in the middle of the night, right when the laser goes multi-mode and you never see it, right? Because you don't have the chance to really check this over and over as you would normally do. And so these guys spent a long time building this laser so it could run basically by itself. As I alluded to, this was made more challenging by the fact that we had like zero money. And as you'll see, our lasers were manufactured in West Germany. They were so old, but these guys did an amazing job. And so about once an hour for 3 years, the experiment sent us an email, and that email had this PDF in it. The stuff over here is sort of laser diagnostics. Here's like the laser spectrum, like it's the frequency, pulse energy. And as the PI, I pretty much just looked at this graph, the rest of it, if I'm honest. This should show, this is the number of collected photons versus time, and you hope to see like a nice big decaying exponential if you see the transition. And we saw nothing. We could set an exclusion that looked something like this. Now, I say here a qualifier. I say there was no obvious long lifetime signal. Right? We expected that this transition would have like a 500 to 1,000 second lifetime. We didn't see anything like that. We did, however, see a shorter timescale signal. If you look at the fluorescence in the first 50 seconds afterwards, here's what you see. From 184 down to 160, which is, I don't know, a year and a half, 2 years, literally saw nothing, which was 0 every day for 2 years. Around 80 V, we saw a little bump. So we took out our crystal that had thorium-229 in it and replaced it with a crystal, this is shown in red, that had thorium-232. Chemically, it's as close as we can get to being identical, but the thorium-232 nucleus doesn't have this transition. And so we see that little bump there, and so that tells you this is either something associated with like a defect with doping thorium into the crystal, or maybe it's an impurity that just happens when you grow. As we kept going though, around 8.3 eV, we saw that this, the fluorescence really started to go up and up. Let me zoom in here. Until we could only, with the current laser system, we could only go down to about 140, what is this? A little bit, 147 nanometers or so. And so that's shown in blue. You see in the 232 dope crystal, there really wasn't anything there. We took out another crystal that had 229 in it, and we also saw that's shown in black, this sort of transition. Now at this time, we had started to, there were other measurements in the field, indirect measurements, mostly from Peter Thyrolf's group in Munich, where they were looking at sort of an electron-enabled quench of the nucleus, and started to say the transition was probably somewhere around 8.4 EV, 8.5, kind of, you know, still a big range, but it was kind of in this region. So we started to think maybe this is the nuclear transition, but our original understanding of the crystal was just incorrect, that it's affecting it more than I showed you in the first slide. So we started working with Anastasia Alexandrova, who's an amazing quantum chemist at UCLA, who I later found out was a postdoc here at the exact same time I was. We never met. And her then grad student, or her postdoc, then postdoc, now faculty in Manchester, Harry Morgan. And they did some amazing calculations. So this is the number of unit cells of our crystal. So this is LISAF, so it's 4 by 4 by 2 unit cells. There's roughly infinity electrons in this calculation. And right here, one of the strontiums has been replaced with a thorium. And the reason you have to do this is these calculations often have periodic boundary conditions. And so if you just do 1 unit cell, then there's thorium everywhere. And so the structure will be different. And so this is like the limit of what they could do on supercomputers. But it appeared to be converged. As you go to smaller, the results don't really change. But you know, DFT is always troublesome. I think that's what the T is for. And so the results I'll show here, this graph is what we call a projected density of states. So these are the electronic density of states projected onto thorium-centered orbitals. These are kind of the electrons we mostly care about because they're the ones that are going to talk to the thorium nucleus. And so you can kind of see some structure. This is like the valence band. This is like the conduction band. It's like a 10 eV gap. And then depending on the configuration here, you can get these sort of in-band states that are just defects associated with doping thorium into the crystal. Thorium is a 4+ charge replacing a strontium, which is a 2+, so there's some extra fluorines that appear and kind of the crystal has to kind of bend a little bit to accommodate it. And you get these defects. And so we started worrying that these states could lead to quenching. And I want to thank Andre here, who's been a longtime collaborator, and his postdoc Bao, who worked on this problem with us. Roughly speaking, the nucleus and the electrons are coupled by what we call a hyperfine interaction, right? Generically, there's spin-spin, there's the electronic field gradient, if you will, can couple to the electric quadrupole moment of the nucleus. And so generically, there's a way for energy to transfer from one degree of freedom to the other. So if you imagine here, I've drawn a line at roughly where we saw this short timescale fluorescence. If you have this much energy stored in the nucleus inside of this crystal, what it can do is it can take an electron below the band top here and just excite it to this defect. And that's a resonant process, as long as there's, you know, states here. And so it goes quite fast. It's first order in perturbation theory. Then this hole can relax very quickly with phonons, and you'd expect to see then some redshifted fluorescence. And this lifetime can be much, much shorter, right, than this thousands of seconds that we had expected. So we said, okay, if this is true, we should be seeing this redshifted fluorescence from the crystal. So we went off to look at that. There was not a lot of signal, so Ricky and James used every filter we had and did some massive Gaussian deconvolution. And the spectrum they reconstructed is shown in blue. So red of 225 nanometers, we see some broad background. That we knew was there already. You can just see that because the crystal does glow a little bit because there's radioactivity inside of it. And we had measured that, and it sort of glows, around there. So that was nice that they saw that. But then we saw a very narrow peak, and we don't really know how narrow it is. This is just, the Gaussian deconvolution says it's narrow. Could be, doesn't really tell you the width. But it was right around this wave. Right at it was actually scarily right on top of what they had predicted. So we had concluded that the thorium-229 in the crystal was probably quenched by this defect hole excitation. And our dream that we had had for over a decade of driving this transition in the nucleus was probably dead, or at least much more complicated than we thought. So we turned our attention elsewhere. And that was partially in response to some beautiful work that came from Peter Tarolf's group at LMU in Munich. Peter did a really cool experiment where he had uranium-233. When this alpha decays, it produces thorium-229. And 2% of the time, that thorium is in this nuclear excited state that we're looking for. And so he then guided that through a quadrupole so that he could only get exactly thorium-229. And then he would soft land it on an MCP detector. When he would do that, the thorium comes off of this uranium as an ion because as it screams out of the uranium, electrons get stripped off. When he soft lands it, it neutralizes. Now, when thorium is neutralized, the energy of the nucleus is more energy than it takes to ionize thorium. And so what it does is the nucleus says, hey, electron, you can have this energy, go away. And the electron flies off and the nucleus relaxes. This is called the internal conversion process. We had predicted this would be a few microseconds, and Peter saw exactly that when he went and did it. So to me, this was really the first proof for sure that this transition existed. All right, like before this, even people, I mean, even after this, some people didn't believe it. But like, if you really were a student of the field, I think there was no way to deny this at this point. And so we said, okay, we know this IC, this internal conversion pathway works. Let's go explore it to do a better energy measurement. And then maybe we can go back and figure out the crystals. So we started a couple experiments that I'll just flash up because it'll be important later. One was what we call the thorium metal search, was in collaboration with Peter and his then postdoc Lars. And then one where we were shooting these thorium into these superconducting nanowire imagers built by Sawu Nam, who sadly is no longer with us, and Galen O'Neill at NIST. And so we were off doing this, and then in May of 2023, this happened. And this was the key. So Pete Van Dupen did a beautiful experiment. It was beautiful and crazy. I know people who were invited to be members of the collaboration and were like, good luck. We're going to do something else. It's like the best kind of experiment, right? What Pete did was he had a crystal. In this case, it was calcium fluoride at first. And he used the ASALDA facility at CERN to implant effectively actinium-229 into calcium fluoride. Actinium-229 beta decays into thorium-229. And when it does, with a sizable fraction, it should feed into this nuclear excited state. And so he then took the crystal, put it in front of a spectrometer just to see if it was glowing, and if so, at what wavelength. And what he saw was a few nanometer wide feature around 150 nanometers. This was exciting for us because this was exactly where we had seen this sort of our quench signal. But it was also a little bittersweet because Pete saw a very long lifetime decay, whereas we had only seen this quenching decay. So we thought, okay, this probably really is the transition, but in our crystals, it's quenched. And in this other crystal, it's just not, I guess. Luckily for us, Peter was visiting us at UCLA. I think we were actually at In-N-Out having a burger. And we said, what? And he was a part of this collaboration. It's like, why don't you take some of our crystal sample back with you? And when you get back to Europe, talk Pete into putting it into the beam. And Pete is amazing, and he just said, sure, and did it like a month or two later. And then a few months after that, Sandro, the lead grad student, called us up and was like, your crystal works too. But probably not all of it. And this was really the key. We had thought, like, if it's quenched, I mean, it's probably like, maybe some aren't quenched, but maybe it's like a part per million or a part per billion. Like, you have no right to expect it to just be like half quenched, right? What they saw was maybe, I don't know, it's hard to get accurate numbers, but maybe like 10% of it is emitting and 90% might be quenched. They didn't really know. And so he said, okay, well, let's go back, because this exclusion I've given you, it always assumed that all the thorium participated. And if that's off, then these exclusions basically are meaningless. So he said, let's do something the statisticians won't let you do. We'll go over this region where Pete thinks a transition is, and let's just look at all the photons we saw, regardless, after each excitation. We drew a mean, and then just drew the mean plus 1, 2, 3 standard deviations. Clearly nothing statistically significant here, but amongst friends, like 2 sigma to 3 sigma is kind of interesting, right? And since it takes like a month to scan this region, we're like, let's just look at these points first, right? And when we went to this point, that was the biggest outlier, we saw a tiny little bump. And it's a few gigahertz wide, which is our laser line width. So this was as narrow as it possibly could have been in our sample. We then put that 232 doped crystal in, and it wasn't there. We said, okay, well, we have the other crystals. So we grabbed the 229 doped crystal from the shelf, put it in, and we saw same thing at exactly the same frequency. And this is really funny because this crystal has more thorium in it than this crystal. So this crystal, only about 1% of the thorium contributes to the signal. And this crystal is probably 100%. It's at least a half. We had 4 crystals. 3 of them look like this. One of them is this one, which we use for 6, 7 years. And sometimes you get unlucky. The universe doesn't care, I guess. But nonetheless, you can now go measure this transition. The frequency, I don't think I'll ever forget, is 2020 407 gigahertz. We had a couple hundred megahertz error bar. It's about 148 nanometers in wavelength. We can measure the lifetime, and it's sort of exactly what we expected. One thing I'll point out, because it's kind of a fun physics problem. It's a great comp problem if you guys still get comps. So this is a magnetic dipole transition. So if you put it in a dielectric, the lifetime gets shortened by n cubed because the density of photon states grows as n cubed, right? So the index of refraction, yeah. If it was an E1 transition, it just goes as n because the electric field would be screened by 1 over n, and then you square it. And so magnetic dipoles, you get an n cubed. And so this says that the bare nuclear lifetime, or the nuclear lifetime is something like 2,000 seconds. There's a big approximate sign here because the index of refraction of this material isn't actually known that well. And so we just, the way you do this is you make a prism of this and send it off to NIST. And so NIST is literally, they just got the prism today, actually. So hopefully we'll be able to turn this into the real number soon. All right, and this was exactly what we'd expected with an error. Now, is this enough to claim you've seen the nuclear transition? In a paper that actually came out a couple weeks before ours, Eckerd Pike, using crystals grown by Thorsten Schum with basically the same idea, found a transition that was 2020 409 gigahertz, but the error bar was about 7 gigahertz. So within error bars, these are the same. Their lifetime was very similar as well. You expect the N in calcium fluoride, because it's such a well-known material, it's actually known, it's been measured by NIST. And so that gives you about a 2,500 second lifetime. And so, within error, these are totally fine. And so, finally, after all these years, I think we could say that we finally have the nuclear transition. And I really think it requires, I wouldn't just claim it based on just our measurement, because even though this is really convincing that you don't see anything in 232, but you do in the 229 dope crystals, they're not really chemically identical. 229 is like an 8,000-year half-life. So these crystals have been sitting there getting color centers and defects induced in them for a long time, whereas the 232 doesn't really have that. But seeing the transition at the same frequency in two different host materials, well, we finally have it. All right, but the world it's never enough, and so after a few days, you're like, okay, what do we do next, right? And the question is, what is the line width that's possible here? Is it really this sort of kilohertz scale thing that we had predicted? Now, this is when June's group entered the fray. June had built this VUV comb that you may have heard about before. It gives you a much narrower laser. It's not really the kind of thing you could use to find the transition, but once you know it, you can go interrogate it. And using these calcium fluoride crystals, he measured, because the nuclear states are 5 halves and 3 halves, and there's an electric field gradient from the crystal, you get effectively 5 lines. There's actually 6 because of mixing, and he saw these 5 lines. The line widths that he's seeing now are of order 10 kilohertz. There may be 40. Most likely that's his laser because they don't know their laser line width yet, but it's at least in the ballpark of what we expected. And I thought I would show this since I was coming back home to Yale. So this is the first poster I ever did on this. Still, I was a postdoc with Dave. And the way this happened, the way thorium-229 happened, this whole idea, was Amar was taking Richard Caston, the nuclear structure guy's class, and he came, and Amar was sitting right next to me. Amar's a professor at Toronto now. He's brilliant. He was like, oh, we just heard about this crazy thing today. There's like a nuclear transition in thorium we learned about in class, and he gave me the paper. And then we were talking in the hallways, and Steve was like, oh, we should put this in a crystal. I mean, in a fiber, I think. It was like, oh, I know people that can put this in a fiber, and we could try to find this transition. Then that night, I was sitting around thinking, it's like, well, maybe not a fiber, but if we put this in a crystal, we could actually do this, and then this could be a clock. And so this was, I like to joke, like July 20, like in this poster, we had calculated all of this. So July to September is not too bad, but it took a little bit longer, I think, than any of us thought. All right, so what's next? The thing I'm really interested in is optimizing these materials and seeing what we can use them for. And one of the hard problems is this crystal growth is challenging. It's a few years to try out any new crystal. And there are problems we want to solve. One is, as we've seen, evidently this nuclear transition can be quenched, right? So we're starting to understand that theoretically, I think. And another is, it's hard to get thorium into stuff. Sometimes you put it in and it just gets spit out when you grow the crystal, right? So there's a few things that we're attacking. One is we're working with Pete now, who can take different crystals and redo his experiment to see if he sees any fluorescence come out of them. And my sort of understanding of the problem now is if you see the nuclear transition in this sort of crude experiment, then it will work, right? And so we've done things that we think shouldn't work and things that do work, and we're starting to build up our lore, if you will. Another thing that would be fun is to use materials that natively contain thorium, because then doping doesn't create a defect because thorium is already part of the crystal. So one of the first materials we thought about back in the day was thorium fluoride, because it has thorium in it. It would be kind of easy to use. But if you go look this up in like the Materials Genome Project, the chemist will tell you very confidently the band gap is 6.537 eV. Right? Turns out that that's just wrong, and it's 10 eV, right? And that was only known like a few years ago. And this is a huge deal for us because it means that our thorium fluoride will work. And so once we realized this, as soon as we found the thorium-229 transition, we wanted to check thorium fluoride because maybe this is a better material. Now, it just so happened that thanks to this collaboration, Lars had then moved to June's lab as a postdoc. June was going to be a part of this collaboration too. And while he was at Gila, Lars built an experiment that could do physical vapor deposition of thorium fluoride and thorium oxide onto surfaces. This is what we needed for that experiment. And so he said, well, why don't we just like try a thin film of thorium fluoride? Maybe it'll work. None of us really thought it would work. But Chong Kun, who is June's senior grad student, is amazing. Literally the next day, drew us 2 samples on sapphire and mag fluoride. Dropped them in the mail, and less than 24 hours later, Ricky and James had them in the beam. And they saw the transition in thorium fluoride. which I say this is kind of, I mean, after a few days, I was very happy about this. But at first I was like kind of annoyed, right? Like we spent like 5 years growing these beautiful crystals. And this is like somebody like stuck some thorium on a microscope slide and it just works, right? But it's really a good thing. You can see the participation fraction, the amount of thorium that participates is very small, right? The signal to noise should have been a lot bigger. I think that makes sense with what we understand now. This is multicrystalline. There's a lot of defects that can lead to quenching. The lifetime's a little bit shorter. We expect that mostly because the index of refraction of these materials that it's coating on and the thorium fluoride are larger. And so you get a quicker lifetime, but it doesn't fully explain this. So there's actually a really interesting mystery here. We can do it on mag fluoride, and it all sorts of works. And I'm really excited about this for the future because if you know about optics, thorium fluoride for many, many years has been well, it's not used as much anymore, but it used to be used as an optical coating for like making mirrors or anti-reflection coatings. This is a review article about all the wonderful things you can do with thorium fluoride films written in 1968, right? So we've been writing review articles for a while. So you can start to think now about making waveguides of this with thorium fluoride in it, building cavities into those waveguides, studying super radiance. I think these are going to be temperature sensors, strain sensors, all sorts of structure sensors that you could build out of this. And right now, this is important because we don't actually need that much thorium fluoride to do this, at least the 229. And there's only about 40 grams of 229 that we can access right now in the world. So we want to use it sparingly. All right. So this just came out like a week or two ago, and it was in collaboration with Andre, my constant collaborator, Anastasia and Harry again, and then also June's group who made the samples. All right, so I got a couple more minutes. Let me tell you about the future. So, the thing that got us excited about this was building a portable clock, or at least that's what paid the bills. This looks great. That's a penny. Right? That's pretty portable. Our laser system is roughly, it actually doesn't even fit on a 5x12 optical cable, right? I like to joke it needs like a coal-fired power plant to operate. Like we're not really going to put this in a satellite and fly it around and look for, bosonic dark matter or something. So what are we going to do? Well, now that we know the frequency, we can start thinking about using nonlinear optics. And no one's ever used nonlinear optics to make this wavelength, but there are a host of materials that look like they could work. And one of them is barium magnesium fluoride. And so the idea obviously is you come in with some easier to make laser, you just double it and you make this crystal. And this is a much easier proposition. You can basically buy a narrow laser referenceable to a cone from Topeka at this wavelength. Right? But you realize you actually don't have to stop there. You could just go ahead and dope the thorium into this crystal because, we've done the calculations, it looks like it should work. And then this has a pretty nice, couple of nice features. The biggest is it no longer requires vacuum, right? Because the VUV is only in the crystal. And so from the clock builder's perspective, I'm giving you a crystal that has a resonance at 296 nanometers, right? And so that could be really, you can imagine putting that in a form factor like this and like flying it around on satellites. So that's something we're working on now. And then I'll skip this in the interest of time. We have time for questions. We're also working on how to quench the nuclear transition to speed up the clock cycle. It looks like we can, looks like we understand it. And I want to talk about something I haven't presented before. And I thought this would be a good place to do it since things started here. So I walked you through this and said, we have this thorium doped into this crystal, and there's this sort of multipole Hamiltonian. We can think about all the perturbations of the crystal on the nucleus, right? And the takeaway is that at the end of the day, there are few kilohertz broadenings that come about from the fluorine nuclear spins interacting with the nucleus. And then there's an inaccuracy of the clock at about a part in 10 to the 16. This is about the definition of the second. And that's because of temperature dependent shifts. And so the question is, can we get rid of those? All right. So to get rid of this, this broadening, we need to get rid of this magnetic dipole-dipole interaction. The problem is you need a really high band gap. And it's hard to get a high band gap without using a halogen, right? We need fluorine because it's very electronegative and all the halogens have nuclear spin. So, thanks to our work with Anastasia on some of this other chemistry stuff I do with molecules, I knew the right words to ask her how to solve this problem. So I want a molecule that replaces fluorine, and I don't want it to have any spin, but I want it to have a big electron affinity. And she had done a lot of work with superhalogens and realized that sulfate can be sort of a stand-in for fluorine. And if you remember your nuclear spins, sulfur and oxygen, you can get them with no nuclear spin. And so this crystal thorium sulfate, they've done high-level GW calculations on, and the band gap is at least 9.1 eV, probably a little higher. And so that's big enough because we don't have to worry about any defects being created because thorium-229 dopes into that without creating a defect. There'll be no states in the gap because thorium's already part of the cell. Okay? These have no nuclear spins. This just goes away. And so then the question is, what can you do to get rid of these temperature-dependent shifts? Right? We kind of always known this, but never really worried about it. But roughly speaking, this chemical shift and the quadrupole shift, at some level, you can think of them as just being proportional to the coefficient of thermal expansion of the crystal. Like at some level, these things depend on the separation. And so at some level, it'll end up looking like alpha delta T over T, some numerical factor, right? And you guys, at least the solid state physics, so if you go to cold temperature, this goes to zero, right? It basically frees out the phonons, everything becomes harmonic. And so we've been looking at this problem now, and it looks like we can get rid of this as well. And so these numbers are highly preliminary. Don't take them seriously because they're absurd. But when you put all this together, the clock instability, this is basically the fraction at which you can determine the frequency of this transition, looks like something like 10 to the minus 23 over the root integration time. To put that in perspective, a 1 micron shift due to a gravitational redshift due to a 1 micron displacement is like 10 times larger than this. So obviously there will be a lot of demons between where we're at now and this, but just to even see numbers like this is pretty exciting. I mean, if that's possible, I don't even know what that means anymore. You could do all kinds of geodesy, all kinds of detection. Yeah, it's just sort of, I mean, optical lattice clocks, all of that stuff, there's like no point for them anymore, if that's true. And then, you could use this to define the second, I think. All right, so with that, I'll stop. Just to give you, I hope you got a sense of, that many people worked on this problem for a very long time. Finally, we have this laser spectrum of the nucleus, and then I'll tell you about where we're headed in the future. So thank you guys for your time. Sorry.
Thanks, Eric. Pretty amazing. Questions? Jack?
I think I'm supposed to use the microphone.
Oh, there you are.
Yeah, just incredible results. One question I had, so nature has sort of provided you with this one isotope, and those people in the 70s happened to notice something in the spectroscopy. Do you know that there are no others, or has this kind of not been studied with sufficient resolution yet?
So, there are a few others that are known. Uranium-235 has something at 76 eV. It's an E8 transition, and the radiative lifetime is roughly the age of the universe. So to drive that, you would have to mix something with it, but maybe that's possible someday. I want to say it's protactinium, but maybe it's something else that starts with a P. May have something around 60 EV, but there's nothing else known.
Yeah, so I know, I understand there's nothing else known, but
is there
have people exhausted the search? Is it possible that there are plenty of others out there that just haven't been studied with enough resolution?
From what I understand, it's been exhausted, and this is it. It's a part in a million chance that this happened. But nuclear structure is a beautiful and challenging field. So maybe it's possible somebody misidentified something, but as far as I know, there's nothing, sadly.
Other questions? So my understanding from the precision, the spectroscopy that you guys did with Jun,
So June did that, not with us. Those were somebody else's crystals.
Ah,
It's like, but-
okay,
yeah, yeah,
apologies.
yeah.
that's
Yeah,
right,
no, I
with
just want to
Thorstein's.
clarify.
Yeah, no, it was Thorstein's. No.
Yeah.
So, that experiment learned something about tiny changes in the shape of the nucleus when it went. Is that right? Or,
Perhaps. So they were sort of already known. People had done spectroscopy of the ion. So you trap the ion and you can, even before we could drive the transition, if you take Peter's experiment, you could trap the ion in the nuclear excited state. And so you can take laser spectroscopy of the electrons and see the hyperfine structure change as it decays. And so they had already measured the moments of that.
I see.
But I think June maybe got the quadrupole measurement a little bit better. Yeah, and so you do have some model now for how much the nucleus changes.
So does that, okay, so then let me put my solid state hat on. So does that mean that if those quadrupole moments are known, now we can figure out the electric field gradients in the crystal?
Oh, absolutely. Yeah, it's trivial. I
And
mean, yeah.
can they be calculated from first principles?
Yeah, so they're not, I mean, so we've done, like, when I say we, that's Harry and Anastasia, they do this calculation all the time. It's like not bad, but like maybe 20% accuracy kind of thing.
I see.
The thing, like, so you can characterize electric field by like a strength along one direction and an asymmetry parameter. Seems like they get the strength right, but usually the asymmetry parameter is, for some reason, just my experience is that that's been harder.
Yeah,
Yeah.
okay.
Yeah.
Other questions? Yes, Anya.
It's pretty naive. So you need a photon with very high energy. Is there any kind of recoil that?
Yeah,
happens?
so this is in what trapped ion people would call the resolved sideband limit, right? The optical phonons are just, the recoil is just not enough to excite them. So like a Lamb-Mossbauer effect,
Right.
is
Yes. Like
zero.
Mossbauer. Yeah.
It's like 10 to the -9 or something. It's super small.
So basically, the sideband is would be too high frequency to.
Yeah.
I see. Okay.
Which is good if you want to build a clock.
Yeah, it's great.
Yeah.
Yeah, that you have most emission in the main line.
Yeah.
I see.
Yeah.
Okay, let's thank Eric again.
Thank you.